So what if you could trick a cancer cell into self-destructing, using the very things it needs to grow? It sounds like science fiction, right? Well, today we're diving into an absolutely fascinating new frontier in cancer research. It's a strategy called ferroptosis, and it's all about turning a cancer cell's own biology against itself. We're going to look at it through the lens of prostate cancer, where it's showing some incredible promise.
First things first, let's talk about the why. Why is this so important? Well, look at this number, 30 to 40%. That's a pretty stark number, and it's the harsh reality driving this research, because that's the 5-year survival rate for prostate cancer once it is spread or metastasized. Now get this, compare that to over 99% if the cancer is caught when it's still localized. That staggering drop is exactly the problem scientists are racing to solve.
All right, so here's our game plan for this explainer. We're going to break down how this whole new approach works. We'll start with the deadly challenge of prostate cancer. Then introduce this wild new form of cell death. After that, we'll get into the mechanism, what we're calling the recipe for cell rust, which is a really great way to picture it. Then, we'll see exactly why prostate cancer is so vulnerable to this and look at how we can create smarter combination therapies. And finally, we'll explore how we can actually see this process happening inside a patient's body.
So, as we just saw, the challenge here is immense. Once prostate cancer breaks out and spreads, even our best treatments, hormone therapy, chemo, radiotherapy, they only extend a patient's life by an average of 2 to 3 years. That's just not enough. There's a critical, urgent need for a completely new angle of attack.
And this is where things get really, really interesting. This new angle comes in the form of a process called ferroptosis. Now, I want you to forget your high school biology class for a second, because this is not the programmed cell death or apoptosis that most of us learned about. This is a totally different pathway, one we've really only started to wrap our heads around in the last decade or so.
So what in the world is it? Well, ferroptosis is a unique way for a cell to die, and it all hinges on one element, iron. It's triggered by a massive buildup of these things called lipid peroxides. But honestly, the simplest way to think about it is like a controlled biological rust. It literally corrodes the cell's outer wall, its membrane, from the inside out until the whole thing just falls apart. And the crucial point here is that this isn't random damage. It's a specific, regulated process we could potentially trigger on command.
And you can really see how different this is when you put it side by side with apoptosis, the classic cell death. Apoptosis is, well, it's neat, it's tidy. The cell sort of packages itself up nicely for disposal. Ferroptosis? Oh no, it is messy. It's defined by that critical need for iron and that rusting process, and it ends with the cell membrane violently rupturing. We are talking about two fundamentally different ways for a cell to die. Okay, so let's take a closer look at this recipe for cell rust. How does this destructive chain reaction actually get started inside a cell?
It really boils down to 3 key steps. First, you need an overload of reactive iron inside the cell. Second, that iron acts like a spark that ignites a chain reaction with specific fats in the cell membrane. These are called PUFAs. This is what creates that widespread rusting. And finally, this runaway process causes such catastrophic damage that the membrane just rips apart and the cell dies.
Okay, so it's a new way to kill cells. But what makes this so incredibly promising for prostate cancer specifically? Well, it turns out this whole process targets one of the cancer's biggest but most hidden weaknesses.
And this quote, right from the research, just gets to the absolute heart of it. Malignant cells are greedy. To fuel their rapid, out-of-control growth, they develop this enormous appetite for the very building blocks of life, especially iron and fats.
And that's the beautiful irony, isn't it? The very things that an aggressive cancer cell craves to survive and thrive, that abundance of iron and specific fats, are the exact ingredients needed to trigger ferroptosis. Its greatest strength becomes its greatest vulnerability. It is essentially addicted to the recipe for its own death.
So this is where the science really becomes a strategy. The goal isn't just to use a new ferroptosis-inducing drug all on its own. The really clever idea is to combine it with our existing treatments to create a much more powerful, synergistic, 1-2 punch.
And this table really just lays out the incredible potential. See, ferroptosis isn't just a standalone idea. It's a way to supercharge the treatments we already have. With hormone therapy, for example, the drugs can actually make cancer cells more sensitive to this rusting process. For chemotherapy, it could be the key to overcoming drug resistance. With immunotherapy, these dying cells can release signals that basically call in the immune system to join the attack. And for radiotherapy, the radiation can weaken the cancer's own defenses against ferroptosis. In every case, it's about making our current tools way more effective.
So the potential is enormous, but there's a huge practical challenge. To actually use this in the clinic with real patients, doctors need a way to see if it's working in real time.
And that's the fundamental question for any new therapy, right? You can give a patient a drug that's designed to trigger ferroptosis, but how can you possibly know if it's actually working on a tumor deep inside their body? How can you monitor the effect without just waiting and hoping?
Well, the answer lies in some seriously cutting-edge imaging. Scientists are developing these specialized tracers for PET scans that can literally light up and track the iron being gobbled up by cancer cells. At the same time, they're creating new contrast agents for MRIs that can detect the telltale signs of that iron buildup. This would give doctors a non-invasive window into the tumor, allowing them to see if the treatment is working and adjust it for maximum effect. It's a total game changer.
So in the end, it all comes back to this one powerful idea. We are learning to turn a cancer's most fundamental characteristics against it. This entire strategy hinges on a single powerful question. Could a cancer's own ravenous appetite for the building blocks of life be the ultimate key to its own destruction?